Hello everyone. This is NagaLakshmi Devi, Assistant Professor, Department of Freshman Engineering, IARE, Hyderabad, Telangana. First topic is Cauchys Integral Theorem. Now here this is not an simple. Now this is not a closed curve. This is simple and closed curve. This one is we are using now. Not closed. Here it is not a closed. The integral limits are maybe A to B like that. This is also not, it is closed but not in completely. Then we are not using this one. Only we are using this one. Simple and closed curve. Always Cauchys integral theorem used in simple and closed curve. Cauchys integral theorem. The first theorem is Cauchys integral theorem. That is, if f of z is an analytic and f dash of z is continuous at every point inside and on the simple closed curve C, then integral over C f of z dz equal to 0. Like this. Now this is the Asian. This is complete Asian. Now closed curve C, the limits are existable in x coordinate and y coordinate. Then this is the Cauchys integral theorem structure. And now the proof is, let f of z be an analytic and f dash of z is continuous at every point inside the Asian on a simple closed curve C, then integral over C f of z e dz. Now the f of z dz is maybe sometimes it will be unequal to 0 or some function is there. We are solving that one. In the condition is, in integral theorem condition is equal to 0. Now we have to prove that one. Now we consider f of z. Z we know. Z equal to x plus iy, and similarly f of z equal to w equal to u plus iv. Now dz equal to, here now differentiating with z, that is dz equal to dx plus I dy. Now substituting that here, f of z is nothing but u plus iv and dz equal to dx plus I dy. Now substituting that one, we get now Cauchys theorem of multiple connected regions. Here we are connecting two multiple connecting regions. Two cycles are there, two regions. Now it is connected with both at a time. Then it is inside the region, outside the region. Both are connected. Then it is under 0 or value. Whatever it may be, you can see here. Suppose f of z is analytic in doubly connected region bounded by the curves C1 and C2. C1 this one and C2 this one. Both are connected, doubly connected here. Then integral f of z over C, C1 dz is equal to integral over C2 f of z dz. Now here PQ is the, here P and Q are the connected path. Is direction of anti-clockwise direction. It is anti-clockwise direction. Compulsory it is an anti-clockwise direction, and sometimes we are using clockwise direction also. Now here f of z minus converted into both sides. Left hand side is converted into right hand side, right hand side is converted into left hand side. We get integral over C1 f of z dz minus integral over C2 f of z dz is equal to 0. Now total is comes under suppose the finite number of simple curves C1, C2 up to so on Cn. Now C1, C2 is there, up to so on Cn curves are there. For example, arranging more curves, then we get C1, C2 up to so on Cn curves. Inside C and f of z is analytic in the region of between the curves C1 and C2 up to so on Cn. Then f of z integral over C is equal to C1 f of z dz plus integral over C2 f of z dz plus up to so on integral over Cn f of z dz. Now this will becomes on each and every term splitting on differently. Now integral over C. Now individually real parts are one side and imaginary parts are another side. Already we know that is u plus iv into dx plus I dy is there. U into u dx plus I u dy plus iv dx plus I into I square value minus 1 minus v dy. Now total real parts, that is u dx minus v dy, and another one plus I into u dy plus v dx. That is we are writing here. Now applying Gain's theorem, we know Gain's theorem, Gauss theorem, Gain's theorem. Now applying Gain's theorem, integral over c f of z dz equal to, now exact solution plus I into exact solution. Now the exact solution means already we know that is exact means dou m dx plus n dy is equal to 0, then it is called exact, in which place we are using exact. Dou m plus dou m by dou y equal to dou n by dou x, then it is called exact solution. Similarly, dou m by dou y minus dou n by dou x is equal to 0, then it is also called it as exact solution. Applying that one here, we get this one. Now the dou u by dou x minus dou v by dou y. Next, similarly, dou u by here, by applying our analytic solution, dou u by dou x is nothing but dou v by dou y, dou x. So applying that one, we get this one. Now, integral over two regions. Integral over the surface of the integrals. Why? Because we are considering two regions, x coordinate, y coordinate. That's why we are considering two regions, dx and dy. Now, the using CR equations we have. Now CR equations, this one. du by dx equal to dv by dy. That's why I am substituting that one here. In these two places, we are substituting that one. Now, finally, we get integral over c f of z dz equal to double integral over r dou v by dou x minus dou v by dou x dx dy plus I into double integral over r dou u by dou x minus dou u by dou x into dx dy. Now the total is 0. This is 0 and this is 0. Total we get the 0. By applying CI equation, Cauchy's Riemann integration value equation, we get the analytic condition. By we get the 0. Simply we are using dou u by dou y equal to minus dou v by dou x. Substituting here, it is minus get plus dou v by dou x minus dou v by dou x. This one is as it is. Now here, dou u by dou x is as it is, dou v by dou y is nothing but dou u by dou x. Substituting that one, we get 0. Total, this is the Cauchy's theorem. Now, Cauchy's integral theorem another way. Finally, we are writing that simply, that is theorem of Cauchy's theorem, Cauchy's integral theorem. Now, this is the Cauchy's integral theorem definition. Let f of z equal to u of x comma y plus I into v of x comma y be analytic on and within the simple closed contour C and f dash of z be continuous theorem, then integral over C f of z dz equal to 0. If within the region we get the value like this. Now the first problem, integral over C f of z dz equal to 0. Now first evaluate integral over C e power z by z minus 2 dz is the given condition, where C of C circle over C mod z equal to 1. Here mod z equal to 1 means the given condition is here given z equal to here z minus z naught, we are treated as z minus z naught here. Z naught is 2. Z is 1. That means z is minus 2. Here 2 is there. Okay. Now the given condition is inside the region. Then that is the 0. Maybe the given condition is outside the region. Then that is value we get. Not equal to 0. That is. If a given condition is z naught is more than z, then it is value we get. Z naught is less than z. Z naught is greater than z is we get the 0. Z naught is less than to z, we get the value. That is the condition. Here earlier also we are seeing that one also, that one. That is the, here this one. Inside the region. Now the inside the region they are given. Now that is becomes on 0. That's why C2 is more than to C1. C1 is more than to Z2. Then that is the 0. If it is this one is less than to C2, then we get the solution of the given function f of z. Simply here we are writing as like this. Here given integral over C e power z by z minus 2 dz. Then z minus 2 equal to 0. Then z equal to 2. Denominator part. then equal to z equal to 2, the curve outside lies the point. Now outside lies the point here. Outside lies the point here. Then the function e power z by z minus 2 is analytic with and on C. Therefore, Cauchys theorem we get integral over C e power z by z minus 2 dz equal to 0. Why? Because here given mod z equal to 1. Actually, the given condition z naught IA, we are treated as anyone. Z naught IA, we consider it is 2. The integral, the given condition point, the function z naught point is 2. But the circle over C is inside the region. We are not we are not supporting this one. That's why it is 0. If it is maybe 3 or 4, we get the value. We have to solve this way. E power z by z minus 2, we get the some condition. Now the integral over C means the total circle is 0 to 2 pi. So applying that integral value 0 to 2 pi, we get the final value. Otherwise it is 0. Now second one. Integral over C z square minus z plus 1 by z minus 1 dz, where mod C, circle C of mod z equal to 1 by 2 taken anti-clockwise direction sense. That here z naught a value equal to 1. That means in the circle that is lies in here, this is origin, this is 1. But the given condition inside the region, that is 2. This is C1, this is C2, that is inside the region. Then the value is 0. Maybe the given function is this mod z, maybe they are given in, for example, 2. That is outside the region, we get the value. They are not given that one. They are given inside the region, that is directly we get the 0. Now, writing like this. Given f of z is z square minus z plus 1 by z minus 1. Now, since z equal to 1, since z minus 1 equal to 0, that is nothing but z equal to 1 is outside C. That is outside C. Yes. Now, f of z is analytic inside C. That is 1 by 2. By Cauchys theorem, integral over C f of z dz equal to 0 directly. If they are given mod z equal to 2, 3, 10 like that, we get the function. We are solving that z square minus z plus 1 by z minus 1 by using any method, we get the solution. By that, now the limits in that condition, the limits are 0 to 2 pi. Now here, but they are not given like that, that's why it is 0. Now the next one. Who that integral over C 1 by z minus a dz equal to 2 pi I, where C is mod z minus a equal to R. Now this is the given condition. R is the region. In x-axis, this is y-axis. Now the circle is there. Now the origin A, we are considering A. Now this is radius R and the angle is theta. Now consider that one. Let A be the fixed complex number A, small a, and P a variable of point Z on the circle. Then AP, then the AP equal to Z minus A. Then the AP, for example, we consider P here, Z minus A. Let AP make an angle theta with the x-axis, then AP equal to R into e power I theta. Directly AP, we are considering this total length is called R into e power I theta. This is polar coordinate conversion. Now final the value is 2 pi I is the final solution. Now how to solve this one means Z minus A is nothing but R into e power I theta. Now this is Z minus A area. Now total is that equal to AP, that equal to Z minus A equal to R into e power I theta. Then this is parametric equation to the circle C, and theta is the varies from 0 to 2 pi. Earlier we know the total circle is nothing but 0 to 2 pi. Always I am talking that one 0 to 2 pi. Now R treated as a constant. Why? Because in the limits are d theta, dz is converted into d theta, that is Z minus A equal to R into e power I theta, that is dz. A is a constant, that is 0, that is R into e power I theta into I into d theta. Now that is the condition. Now total this is dz equal to I R e power I theta d theta. Now integral over C 1 by Z minus A dz is converted into over C is 0 to 2 pi. Completed. Now dz equal to I into r into e power I theta d theta. That is also completed. Z minus a is nothing but I into e power I theta. Substituting that one. Next step. Now integral 0 to 2 pi I d theta. Why? Because in earlier it is r e power I theta, r e power I theta get cancelled. Remaining I r d theta is there. Now here r also cancelled, only I d theta. Now I d theta means integral 0 to 2 pi d theta is nothing but I into theta. The limits are 0 to 2 pi. Applying 2 pi, upper limit minus lower limit, we get I 2 pi I. That is the final solution. Here is the small I. That is the final. Now the next problem. Verify Cauchys theorem for the function f of z that equal to 3z square plus iz minus 4 if c is the square with vertices at 1 plus or minus I comma minus I minus 1 plus or minus I. This is the given conditions. Here we are considering is 1 plus or minus I comma minus I plus or minus I means total. This is the complete circle. Given f of z is 3z square plus iz minus 4. Now considering the boundary square consists of 4 curves, that is C1, C2, C3, C4. That is C1, C2, C3, C4. Total 4 curves are there. Now total curves converted into overall complete circle means C1 plus C2 plus C3 plus C4. Now the condition existable for C1 along, for example, we are considering that is the total condition like this: C1 to C2, C3, C4. C1 the given condition is minus 1 to 1. Now this is the minus 1, this is 1. Next C2. C2 is totally C2, C1 to C1. Now the condition is, for example, we are considering the given function f of z equal to complete converted into xys. Why? Because C1 to C2 is parallel to the x-axis. That's why total the given equation is converted in terms of x. Now the function is 3z square plus this one, then converted into C1 along the curve y equal to 1. Here y equal to 1 and xy is from minus 1 to 1. Xy is from minus 1 to 1 and y equal to 1 only. That is dy equal to 0. Then dz equal to dx. What is that one? Z equal to x plus iy. Dz equal to dx plus I into dy is nothing but 0 here. That is dz equal to dx. That is the substitution here. Dy equal to 0. Now integral over C1 f of z dz equal to, the limits, x limits are minus 1 to 1. 3 into z is nothing but x plus I. Y value here, it is substituting y here. X plus I into y equal to 1. Z is nothing but x plus I whole square plus I into z in the condition. That is x plus I minus 4. Dz equal to dx. The condition is 3z square plus iz minus 4 into dz. That is the given function f of z. 3 is as it is. Z is nothing but x plus I. Substituting that one. X plus I minus 4 into dx is nothing but dz. Dz is nothing but dx. Now limit in integration. 3 into x plus I whole square. That is x plus I whole cube by 3. Plus I into x plus I whole square by 2. 4 into x, 4x. The upper limit minus lower limit. 4 minus 1. We get the 14. That is the final of C1 over C. Next, similarly, along with C2, now x1 along with C2 means that is parallel to the y-axis. Okay. Now the y limits are parallel to the y-axis. Now the y limits are minus 1 to 1. All the limits are x and y are both are same. Why? Because this is always 0. This is minus 1. This is 1. Now here it is also 1 minus 1. The limits also they are given I plus or minus 1 plus or minus I. 1 minus 1 plus or minus I. The limits are given like that. That's why we are considering like this. Now, here dx equal to x equal to minus 1. X equal to minus 1, then dx equal to 0. Similarly, substituting that one. Same process. Now, the same process, z equal to x plus iy we know. Now, x is nothing but minus 1. Minus 1 plus iy, z equal to. Now, dz equal to, this is 0 plus I dy. dz equal to I dy. I am substituting that one. dz equal to I dy. Integral minus 1 to 1, 3 into z is nothing but minus 1 plus iy. Iy minus 1, whatever it may be. Both are same, na? That's why. Next, plus I into z. Iy minus I. Minus 1, this one is 1. Minus 4 into I dy. The total is minus 2 plus 4i. Upper limit minus after integration, we get that one. Now, similarly, C3. C3 is parallel to the x-axis again. Parallel to the x-axis. Now, here y equal to minus 1, dy equal to 0, and xy is from minus 1 to 1. Now, substituting. Z equal to, now z equal to again. Again, we can see, check it and z also. Z equal to x plus iy. That is, x is as it is minus iy. I value minus 1, na? That's why x minus y, z. Now, dz equal to dx. Now, substituting that one. dz equal to dx. Now, ix only. Here, 3x into, now minus 1 is there, x minus y. This is x minus y. X minus, I minus x. No. X minus I. This is x minus I. X minus I. Here it is x minus I, na? X minus 3 into x minus I whole square plus I into x minus I minus 4 dx. Now, substituting this one, that means integration part, 3 into x minus I whole cube by 3 plus I into x minus I whole square by 2 minus 4x. Upper limit is 1 and lower limit is minus 1. The limits are minus 1 to 1. Finally, we get the minus 10 is the C3 value. Now, similarly, C4. C4, x equal to 1. Now, dx equal to 0. The y limits are the same. Z equal to x plus iy. Z equal to x value 1 plus iy. dz equal to, this is 0 plus I dy. Now, substituting z equal to 1 plus iy and dz equal to I dy. Substituting 1 plus iy whole square plus I into z value. 1 plus iy minus 4. Totally, we get minus 2 plus minus 4i value. Now totally, integral over c f of z dz equal to integral over c value, integral over c2 value, c3 value, c4 value. Finally, we get the solution is 0. Hence, theorem is verified. That means this is Cauchy's theorem is satisfied. What is the Cauchy's theorem? The f of z dz equal to integral over c, f of z dz equal to 0. It is satisfied. If it is, we get the another solution minus 1, minus 10, 10, 15 like that. That is not a Cauchy's theorem. That is some function. Now the another one. Similarly, here also we are using that one. Integral over c, z plus 1 dz equal to 0 over c, where c is the boundary of the square whose vertices at the points z equal to 0, z equal to 1, z equal to 1 plus I, z equal to I. Total this one. We condition like that. Now the another one. Integral, if c is the boundary of the square with the vertices at a point z equal to 0, 1, z equal to 1 plus I, z equal to y, and another f of z is completely changed. That is 3z plus 1 into dz. The limits are same. The function is different. You can prove that one. Now the another examples. Now, prove that integral over c dz by z minus a equal to 2 pi I. And another one is z integral over c z minus a whole power n dz equal to 0. Where n is any integer not equal to minus 1. Where c is the cycle. Where c is the cycle in z minus a area that equal to radius r. Now the solution. The parametric equation of the cycle C is mod z minus a equal to, already we know that is r into e power I theta Earlier we are finding that one. Z minus a is nothing but r into e power I theta, where theta is varies from 0 to 2 pi. Now same problem, substituting that one, we get 2 pi I. Same that method, but the difference is z minus a equal to r, we are treated as that one only. In earlier we are not considering that one, we are considering that one, that is 2 pi I. Now e power, for example, they are given e power 2 of n plus 1 into theta pi I, whatever it may be, e power 2 n plus 1 is, we get the 1. Now next one, this is completed, and next one, integral over c z minus a whole power n dz equal to 0, where n is the integer and it is not equal to minus 1. Now the substituting, integral over c value is 0 to 2 pi. Z minus a I into e power I theta. Maybe z minus a whole power n ante, that is nothing but n is there. We get, maybe this is r power n, e power I theta power n. I am substituting that one. Now here z minus a equal to r e power I theta, dz equal derivative with respect to that one, a, we get with respect to z, we get dz, a treated as a constant, r is a constant, e power I theta into I d theta. Similarly, z minus a whole power n into r power n e power I theta power n means r power n is treated as a constant, e power I theta into n, that means n minus 1 into n into I into d theta. I am substituting that one, IR theta d theta. Now two r's are there, r power n into r is there, that totally r power n plus 1. Now that one is this one, n plus 1, n plus 1. Now totally we get, now this is minus 1. Here two terms are there, e power I n theta into e power I theta. Bases equal, we are adding the powers, we get e power I into n plus 1 theta d theta. Now I into r power n plus 1 is a constant. Now integrating this one, e power theta, e power 2 theta, integral of e power 2 theta d theta is nothing but e power 2 theta by 2. Similarly here I of n plus 1 is a constant, that is by I into n plus 1. The limits are 0 to 2 pi. Now why we are considering n is not equal to minus 1 means, here n equal to minus 1, the denominator is 0. Something by 0 is, we get infinity. That's why the condition is given. Not equal to minus 1 condition is given like that. Now I into r power n plus 1 by I into n plus 1. I get cancelled, remaining r power n plus 1 by n plus 1 into e power, now this is 1, e power I n plus 1 into theta is nothing but 2 pi. Substituting that one. Now upper limit minus lower limit. E power 0. E power 0 value is 1. That's why 1. 1 by I into n plus 1. Overall we are common with 1 I into n plus 1. I get cancelled, remaining r power n plus 1 by n plus 1 into e power I into n plus 1 2 pi minus 1. Now this is nothing but 1. And this part is 1. Minus 1 is there. Total this is u. E power 2 into n plus 1 of pi value is 1. That 1 substituting here, 1 minus 1 is 0. Total 0. We get this is 0. Z minus a whole power n dz equal to 0. Cauchys theorem is satisfied. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.